In this video, we will be practicing solving trig equations, both linear and quadratic. Here are kind of in general the steps that we will be using. So we need to first, if needed, simplify the equation so it's in terms of one trig function. The only time we would really see two trig functions is if it was something that could be like factored by grouping, right? Normally we want it all in terms of sine or all in terms of cosine. Then we need to solve the equation so that we have a single trig function of an angle equal to a constant, equal to a number. If it's a quadratic, you'll have two of those cases, right? You'll break it down into two linear things by looking for patterns that allow you to factor using difference of squares, square rooting, or any factoring opportunity. Then we write down the possible values for that angle, okay? So we're not really paying attention to what's inside the sine, cosine, tangent at this point. We're just thinking, okay, tangent of what gives me that constant? Cosine of what gives me that constant? Sometimes if we have like a 2x, a 3x inside of the argument, it helps to substitute in something else, okay? Then once solved, if needed, substitute the trig expression back to then solve for the actual variable that you were, solving for. And then at the end, just apply any restrictions that there may be and then write the solution in general form. Okay, so we're just going to do some examples starting with this one. We have 2 sine of z over 4 is equal to radical 3, and we're looking from 0 to 16. And the first thing I notice before I even start solving is that z over 4, that period has been stretched, right? When we look at sine of theta, the period is just 2 pi. And we find the period by doing 2 pi divided by b. So sine of theta over 4, my period is going to be 2 pi over 1/4, or my period is going to be 8 pi, which means that every 8 pi, my solutions repeat themselves. So it has been stretched, but my interval is still double the period. So I should expect 4 solutions, because normally there's 2 solutions in one period. I've doubled the period as my interval, so my expectation should be 4 solutions. And you can kind of think about that at the end. I like to think about it at the beginning. But let's go ahead and solve for sine, right? The first thing you need to do is isolate the trig expression. So I have sine of z over 4 equals radical 3 divided by 2. Okay, and this is what I was talking about earlier on the last slide, that you may want to substitute a variable in, because really all we're doing here is we're going to say let z over 4 equal theta. Okay, so then the problem becomes sine of theta equals radical 3 over 2. And then rather than asking ourselves, having to pay attention to this, what angle divided by 4 is then radical 3 over 2, I can just ask myself, where is the sine of an angle radical 3 over 2? And so that means that I'm going up, right? Sine of radical 3 is when you go the distance, you go up, but it has to be positive. So that's going to be pi over 3 and 2 pi over 3. But notice that those are my thetas, right? That's just sine of pi over 3 is radical 3 over 2. But if I plug in pi over 3 to my original equation, pi over 3 divided by 4 is pi over 12. And the sine of pi over 12 is not radical 3 over 2. So it's important that we substitute back, right? We said that theta was z over 4. Well, now we know what theta is equal to. So now we can say that z over 4 equals pi over 3 and z over 4 equals 2 pi over 3. Okay, but what to keep in mind is that these might not be the only solutions, but let's solve for z first. So the way that I would solve for z is I would just, multiply both sides by 4. Okay, so I would get that 2 of my solutions are z equals 4 pi over 3, and z equals 8 pi over 3. Right? But notice 8 pi over 3 is a lot less than 16 pi. I like to write everything with the same denominator so that it's easy to compare. 16 pi is 48 pi over 3. And 8 pi over 3 is way, way less than that. So we should probably continue to check if there's more solutions. And again, I already know that there's likely to be 4 solutions because I've doubled the period, and normally I have 2 solutions per period. So I need to take my solutions. I have 4 pi over 3. I need to add a full rotation because that's when they start to repeat themselves. So a full rotation is 8 pi, but 8 pi is the same as 24 pi over 3. So again, it's easier to think about things when they have a common denominator. So because the period's been stretched, the solutions are much further apart as well. So that gives me 28 pi over 3, which, yes, is less than 48 pi over 3. So now we have 3 of our solutions. And then let's take 8 pi over 3 and add 24 pi over 3. And yes, we get 32 pi over 3, which is less than 48 pi over 3. And now we'll see that if I was to add 24 pi over 3 again, that's going to be greater than 48 pi over 3. If I add 24 pi over 3 here, that's going to be greater than 48 pi over 3. So I'm done. I found all my solutions on this interval. So my answers are z equals 4 pi over 3, 28 pi over 3, 8 pi over 3, and 32 pi over 3. Okay, let's try another. This one is quadratic. I noticed that I have a squared term, a linear term, and a constant, which normally tells me that it's just going to be, put in standard form, ax squared plus bx plus c, and I'm going to be able to factor it. So the first thing I need to do is I'm going to move that 3 over to the other side. So now I have 2 cosine squared of 3x plus 5 cosine of 3x minus 3 equals 0. And even before I kind of isolate the trig function by factoring, I'm going to do a first round of substitution. And I'm going to say, let's let cosine of 3x equal t. So if cosine of 3x equals t, that turns this equation into 2t squared plus 5t minus 3. Equals 0, which many people, including myself, think is easier to factor, right? Even if I don't write that out, that's kind of what I'm picturing in my head. Okay, so when I factor this, I know it has to be 2t and t. I know it has to be 3 and 1, right? So either a 3 or a 1 or a 1 or a 3. And 1 has to be negative, 1 has to be positive. So I'm going to put positive 3 here because I want 3 times 2 to give me 6. So I will put the positive 3 here and the negative 1 here. Okay, and you could go so as far now to solve this and say, okay, t equals 1/2, t equals negative 3, and then substitute back. But you can also rewrite it in factored form and say, okay, that's 2 cosine of 3x minus 1 and cosine of 3x plus 3, and then set them equal to 0, right? But for each one, when I set it equal to 0, you'll notice I get the same thing as I did above, so it's sometimes easier to substitute after you solve. I would get that cosine of 3x, which is the same as t, is equal to negative 3, and after adding 1, dividing by 2, I would get cosine of 3x equals 1/2. Okay? So now we do our second round of substituting, and we can say, okay, now let's let 3x equal theta so that we can solve for just the angle. So really I'm asking myself, where is cosine of theta 1/2, and where is cosine of theta negative 3? Well, the first thing is that this never happens, right? Cosine is never -3. The range on cosine is 1 to -1 or -1 to 1. Unless the amplitude has been changed or it's been stretched, the highest it goes is 1 and the lowest it goes is -1. So that never happens. So that doesn't give us any solutions. So then we think about where cosine is 1/2. Cosine is going to be 1/2 when I just barely go over, both going up and going down, right? Cosine is positive in quadrants 1 and 4. So that gives me that theta equals pi over 3 and 5 pi over 3. But notice I wasn't given a restriction. I wasn't given a restriction on this. So really I have all my solutions I need to give. So I need to say that every 2 pi k, these are repeating themselves, right? Where k is just any integer. You could say k is in z, right? That means that little z is basically integer, so it's saying k is an integer. And that will give me all my solutions that repeat, because remember, every 2 pi, it loops again, and you have a coterminal angle that has the same cosine. But that was theta, not x. I need to solve for x, so I have to unsubstitute again, right? I said that theta was 3x, so now I need to take 3x and put it where I see both of my thetas. So I'll have 3x equals pi over 3 plus 2 pi k. Keep jumping the gun there. And 3x equals 5 pi over 3 plus 2 pi k. And then to solve for x, I need to multiply both sides by a third. I think it's easiest to multiply by a third as opposed to dividing by 3, because all of them, there's fractions involved already. So I will get that x equals pi over 9 plus 2 pi k over 3 and 5 pi over 9 plus 2 pi k over 3, where k is any integer. And now this one is done. All right, let's do one more. This one is on a restriction again. It's cotangent and it's linear. So because it's linear, I'm going to start by just isolating the variable, getting the variable by itself. So I'm going to subtract, or not the variable, the trig function. I'm going to subtract 7 radical 3. So now I have 7 cotangent of 2w equals -7 radical 3. Then I'll divide both sides by 7, and I will be left with cotangent of 2w equals negative radical 3. So again, we can do some substitution. And for this part, a lot of people just kind of substitute in your head, but it's important that you remember to, change it back. I'm going to let 2w equal theta. So now I'm asking myself, not cosine, now I'm asking myself where cotangent of theta is negative radical 3. Well, remember, for it to be negative radical 3 in the numerator, after keep change flipping, that means that I would have had negative radical 3 over 2 over 1/2, right? Because if I keep change flip that, the 2's are going to cancel and it will leave me with negative radical 3. Well, cotangent is cosine over sine. It's negative. Cotangent is negative in quadrants 2 and quadrants 4. So that means that I'm looking for a cosine of radical 3 over 2 in quadrants 2 and 4. So when I sketch that, it's going to give me 5 pi over 6 and 11 pi over 6 as my two thetas. So I have that theta equals 5 pi over 6 and 11 pi over 6. But remember, I substituted out. So I need to substitute back in and change out the theta for a 2w. So I will go back and say, okay, now 2w equals 5 pi over 6 and 2w equals 11 pi over 6. Now notice I didn't write the 2 pi k here because I have a restriction. So I don't know how many solutions exactly I'm going to have yet, but I have a restriction. So I need to see what the first solutions are and then, find the others. So I'll multiply by 1/2. I'll multiply by 1/2. Okay, and that will give me that W is 5 pi over 12, and W is 11 pi over 12. Okay, when I think about 5 pi over 12, is it greater than pi over 3, right? Because my restriction starts at pi over 3. So let's take a look at pi over 3 with a denominator of 12. Pi over 3 with a denominator of 12 is going to be 4 pi over 12. So 5 pi over 12 is greater than it, so it does fit into my range. And then 2 pi is going to be 24 pi over 12. So certainly I have some room to grow because 11 pi over 12 is much smaller than 24 pi over 12. Let's keep in mind that the normal period of cotangent of theta is pi. So cotangent of 2 theta is going to have a period of pi over 2. And that means that solutions repeat themselves every pi over 2. And it makes sense because the distance between these two is pi over 2, right? That would be 6 pi over 12. So I just need to add 6 pi over 12 until I get there, right? It wouldn't make sense to add it to 5 pi over 12 because I already have that one, 11 pi over 12. So we'll take 11 pi over 12 and add it to 6 pi over 12. That will give me 17 pi over 12. And then we'll take 17 pi over 12 and add it to 6 pi over 12, which will give me 23 pi. 23 pi over 12, which is just one less than 24 pi over 12. So that's going to be the last one on the interval for us. So our solutions are that W equals 5 pi over 12, 11 pi over 12, 17 pi over 12, and 23 pi over 12. And that is all I have for this video. Hope it helped.